right, this is CH203, and we're at the point now where we need to review for exam number 3 on chapter 7 and 8. 7 covers gases, liquids, and solids, and 8 covers solutions. So first thing I want to do is share my browser screen and point out a couple of things in Blackboard. So I'm going to call, I hope I can find it. Here we go. All right, so let me switch tabs here. We need to go to, nope, there. Okay, so here's your, this is what you would see when you enter Blackboard, the Blackboard course. And I'm going to scroll down, and you'll see some things here that won't show up on yours because I'm in instructor mode. But in fact, I should go into student preview mode. There we go. So now we go down to learning modules, and then we scroll down to exam 3 here. Of course, these are all the videos, the lecture videos, part 1, part 2, and lecture chapter 8. Okay. Now, where's the exam? Okay, the exam may not, okay, the exam's not going to show here. There will be a link to the exam, and you have to get to that, of course, through Lockdown Browser. But what you need to do first is go into Blackboard, this course, in your standard browser, not the Lockdown, and print out this file. This is your periodic table, and print out this file, which is solubilities of common salts. Periodic table, you've seen one of those before, so you know what it's going to look like. But this one, as a reminder, is going to be, well, I'd have to reshare that, but just download it and print it, so you'll have it for the exam. A couple of questions, you will need this information. Okay, so let me see, I'm going to exit that preview. And why don't I go down here, and since I'm in instructor mode, and see why the exam was not showing. Okay, it's an adaptive release, which means okay, this exam will not be available unless you have taken exam 2. If you skipped exam 2, then you won't see this one. So you're just shooting yourself in the foot if you don't take all the exams. If you think you're going to skip to the end and take the last exam and maybe the final and pass the course, you're mistaken. You have to take every exam. And this one will not open until you've taken exam 2. Exam 2 won't open unless you've taken exam 1. All right. Similarly, exam 4 will not open until you take this exam. Just a word of warning. All right, so I'm going to stop that share. And now I'm going to share, I've got 2 documents, one for chapter 7 and one for chapter 8 with sample questions. And I'm going to use those, some of those questions for the review process. All right, so let me share. This is the correct one. And there you go, chapter 7. Notice it looks exactly like an exam. You have multiple choice questions. And we're going to use that to open discussion about these topics. Okay. So I've got some picked out, and the first one I'm going to look at is number 2. And let's see, for the benefit of our viewing audience, which is everybody, Chapter 7, number 2. In which of the following groupings are the 3 terms closely related? All right, so you have to look at each one and see which ones make sense. Kinetic energy, energy of motion, cohesive force. Okay, kinetic energy is energy of motion, but it's not a cohesive force. Remember our discussion, cohesive force versus disruptive force. The cohesive force is assigned to potential energy, and the disruptive force is assigned to kinetic energy. So with that in mind, A, of course, is false. B, potential energy, energy of attraction, those are both true, but it's not a disruptive force. It's a cohesive force. So B is false. How about kinetic energy, electrostatic interactions, and disruptive forces? Disruptive forces and kinetic energy are true, but electrostatic interactions are assigned to potential energy. So D must be it. Let's see. Potential energy, electrostatic attractions, and cohesive forces. Those all 3 are discussing the same topic. They're all related to potential energy. Now remember why we're interested in potential versus kinetic energy. Right? Potential energy tends to hold substances together. Kinetic energy tends to push them apart. So when you have a solid, which one dominates? For a solid, that one dominates. Potential energy, holding things together in that form. For kinetic energy, that dominates for a gas. So your gas is dominated by kinetic energy. Potential and kinetic energy tend to balance for liquids, somewhere in the middle. Okay? All right. So that was our first one. Let's skip down to number 4. The phrase is particles close together and held in fixed positions. That refers to one type of phase of matter. Completely fills the container refers to a different one. So which ones are the right combination? The first one references solids. So we look for solids. There's only one that says solids, this one right here. And let's see if that matches gases. Completely fills the container. Exactly right. If you put a liquid in a container, it will take the shape, but it will not take the volume. But a gas will take both the shape and the volume. A solid doesn't need any help. It's got a shape and it's got a volume that are self-contained. So B is the answer for 4. Solids and gases. All right, let's see. Let me make sure we stay on screen here. There. All right, next one I got picked out is 5. Let's see, I got something in my way here. Let me move it out of the way. Okay. For number 5. How many times larger in size is atmosphere pressure unit than millimeter mercury pressure unit? All you need to know to answer this question is, what's the equivalence? Right? You've got a conversion factor here with an equivalence. 1 atmosphere equals what? 760 millimeters of mercury. So the answer has to be 760. How many times larger is millimeter mercury pressure unit? So that's C. All right. So next one I want to look at is 7. There we go. Scroll to 7. Indicate what the missing words are in the following statement of Charles' law. Okay, so you have to remember what Charles' law is. Remember? Charles' law relates volume and temperature, and that's equal to a constant. Or you can do the before and after version. That's before, and that's after. In that case, you don't need the constant. Because if this one is equal to the constant, that one's equal to the same constant, they're equal to each other. So let's get back to the question. The volume of a gas sample is what? Proportional to its what temperature? Anytime you see two variables that are in a quotient relationship, that is one divided by the other, and that's equal to a constant, that relationship is always direct proportional. Okay, so it's either A or B. Then we have to consider temperature. Temperature here is referenced in terms of what units. The only way that this law works is with temperature in Kelvin, not Celsius degrees. So that means 7 is B, directly proportional Kelvin temperature. All right, what are the other laws that we've studied? Right, that was Charles' law. How about Boyle's? Robert Boyle's law. Pressure times volume equals constant. This is volume temperature equals a constant. And those are different constants, of course. What else? Avogadro. Avogadro's law relates volume and moles. Okay? And then what happens when you put them all together? You get the combined gas law. That's equal to a constant also. But this is the more useful version. The before and after. Okay? All right, so let's get back to the questions. We want to go to number 9. The correct form of the equation for the ideal gas law. I didn't put that one up here. So what do we normally write for the ideal gas law? Pressure times volume equals moles times a constant times temperature. That's the typical arrangement, which would be A, correct? That's it right there. All right. Next one to look at is 10. What is the volume in liters occupied by 2.12 moles of nitrogen gas at 0.745 atmospheres and a temperature of 55 degrees Celsius? Okay, when you get a problem like this, word problems, they are specifically designed to confuse. They give you a whole lot of information, incorrect English syntax, of course, but that doesn't help you with solving a problem. You've got to extract the information from that problem, put it in a form that's mathematically soluble. So moles is equal to 2.12. And this is nitrogen gas. That may be necessary and may not be. Right? When we're talking about gas laws, unless you're discussing a chemical reaction, it doesn't matter what the gas is. If you're just solving a gas law, a gas is a gas is a gas. So, and we've got 0.745 atmospheres pressure. 745 atmospheres. That's moles. Okay, what else do we have? Temperature. All right, what do we know about temperature? If you're going to solve a problem with gas laws, the temperature has got to be Kelvin. So you've got to add 273 to it. So that's be 8. This will be 12, 328 K. Okay. Now you have all the information you got up there except for the question. What's the question? We want to know the volume in liters. So what are we talking about here? We've got to decide, is this a before and after situation, or is this a state function? Is this the state of the gas right now? This is the state of the gas now, because you're not given two values for any of these. You're only given that value. So that means you need to use the ideal gas equation. Now that you recognize that, what other information do you need? Right? You got this one. You got this one. You got that one. You need to find this one. What one do we not have yet? That one. Memorize it. R equals 0.08206 liter atmospheres per mole K. And if you work enough of these problems, you will automatically memorize that number. If you work one and say, okay, I'm happy, you won't remember that number come test time. Okay, so we're going to solve for volume. There you go. Okay, so we just fill in our values, right? Moles. I'm going to leave the units out for space, to save space. R and T, 328, divided by pressure, which is 0.745. Okay, that's the hard part. That requires thinking. Now it's number crunch time. 2.12 times 0.08206 and times 328 and divided by 0.745. So I get 70, let's see. That's only two significant figures. 777, rounded off 77.6. No, 76.6, excuse me. This one. So C is the answer. Now, why do we know that's in atmospheres? Because of these units. Excuse me. That's not atmospheres. That's volume. We know it's liters because liter atmospheres mole K is the constant. So this one has to be in moles, that one has to be in K, and this one has to be in atmospheres. If it's not, if you're not given those units, you've got to change them. So you need to know conversion factors. If this were given in millimeters of mercury, you would divide by 760 because that's how many millimeters there are in one atmosphere. If the answer were in milliliters, you solved it for liters. How many milliliters is that? That's not, of course, this is the correct answer. But if you needed milliliters, like that. Okay. I'm in class. That was number 10. All right, let's look at number 11. The partial pressure of helium in a mixture of helium and nitrogen trifluoride. So you got these two gases and nitrogen trifluoride. Okay. What's the partial pressure of helium? What does that mean? Is it A, the pressure that the helium would exert in the absence of nitrogen trifluoride? That's exactly right. The partial pressure means that. That is the definition of partial pressure. What pressure would that gas exert if all the other gases were absent? Now, why are we interested in partial pressure? Because of what Dalton said. The partial pressure in this case, the total pressure would be the pressure due to helium plus the pressure due to nitrogen trifluoride. Okay? That's a law. That's Dalton's law of partial pressures. But the answer to 11 is A. We didn't even have to look at the others. All right, let's skip down to 14. Which of the following is not a factor? Okay, it's important to read these questions carefully. Sometimes they're in the positive, sometimes they're in the negative. This is in the negative. Which of the following is not a factor in determining the magnitude of the vapor pressure of a liquid? Right? What determines the vapor pressure of a liquid? Right? Vapor pressure of a liquid is determined by temperature. Okay. How about the nature of the compound itself, which means intermolecular forces? So at the same temperature, one gas might have a higher vapor pressure than another one. Oh, what is the vapor pressure? If you put the liquid in an enclosed vessel, cap it, then eventually evaporation and condensation will become equal. Right? You'll lose molecules to the atmosphere above, and then they'll reach a point where they'll start returning. And when they return at the same rate as they leave, you have equilibrium. The pressure at that point is the vapor pressure. Okay. So if you have the same temperature for two different liquids, right? You have liquid 1 and liquid 2. And the one on the left has a higher vapor pressure than the one on the right. They're at the same temperature. What's the difference? The difference is one has lower intermolecular forces holding it together. 2 has the higher intermolecular forces. Okay, let's see if that helps us answer the question. The temperature, let's see, which of the following is not a factor? Temperature of the liquid is a factor, right there. The strength of the attractive forces between molecules of the liquid, that's the intermolecular forces. That's a factor. Right? The size of the container for the liquid is not a factor. Doesn't matter how big the container is. As long as you have liquid here and vapor there, it will develop that same pressure at a given temperature for the same liquid. All right. So C is the false statement. And the types of forces between molecules is another way of saying B. Well, they're corollaries. B and D are related. But the false statement here, the one that answers the question, is C. The size of the container doesn't matter. You will continue to lose liquid until that vapor pressure is established. The only thing that would negate that statement is if you completely lose all your liquid and there's not enough liquid to reach equilibrium, right? But that wasn't part of the question. The size of the container for the liquid doesn't matter. All right, well, that was 14. And the answer for 14 was C. All right. Let's go down to 16. Here we go, jumps across a page. A liquid is placed in a closed container. Equilibrium is reached when? All right, I've already answered the question. Let's see if we can find it here. All the liquid evaporates? No, if all the liquid evaporates, you're not going to reach equilibrium. When the rate of condensation equals the rate of evaporation. That's the answer right there. When the rate of condensation returned to liquid equals the rate of evaporation. While we're here, that was 16 and the answer is B. While we're here, let's review the names and definitions for the different processes that occur in phase changes. Right? So if you have a gas here, and you have a solid over here, and you have your liquid over here, okay? What phase changes can occur? You can go from liquid to gas. That's evaporation. Or you can go from gas to liquid. Pardon me. Okay, back to our discussion. A liquid can evaporate, or the gas of that liquid can condense. Okay? A solid can do what? Let's see. To be consistent, inner was like this. The solid can melt. Or it can, let's see, solidify. There's a better word for it than that. All right, we'll do that for now. There's a better word. I'll think of it in a minute. This one, the gas, the solid can sublimate. Or it can deposit. Okay, so those are the processes that can occur among these phases. And we'll need that to answer some subsequent questions. Okay, so we're on 16. A liquid is placed in a closed liquid container. Equilibrium reaches. Oh, we already did that one. 16's done. We need to go to 17. Liquids will boil at lower temperatures. A liquid boils at lower temperature when it's at higher elevation because. Why is that? Because remember what happens in a closed container. The evaporation of the liquid is eventually reached. You eventually reach the vapor pressure. If you reduce the pressure in the atmosphere above, say you open the vessel, then the only thing that's holding the vapor molecules down is the external pressure. So at higher pressure, it's easier to evaporate. At higher altitude, excuse me, at higher altitude or higher elevation, it's easier to evaporate because there is less resistance from external pressure. So why does it boil at a lower temperature? It doesn't take as much energy to liberate liquids into the gas phase. The atmospheric pressure doesn't increase at higher elevation. The atmospheric pressure decreases. The vapor pressure at which boiling occurs is lower. Right. So we have to define what we mean by boiling also. Boiling is a special case of evaporation. When you, let's see, where am I? 17. When you increase the temperature on a liquid to the point where you start getting gas phase forming inside the liquid, at that point, the vapor pressure of the liquid is equal to the external atmospheric pressure. So if you have 1 atmosphere here bearing down, then when you reach the temperature where these two balance, where the vapor pressure of the liquid balances the atmospheric pressure, that's the boiling point. Now, if that occurs under 1 atmosphere of pressure, exactly 1 atmosphere, that's the standard, not the standard, the hold on a second. I just saw it not long ago. maybe it's right here close. Or maybe I missed it. Okay, that's the standard boiling point. Any boiling point can happen at different external pressures, like top of Mount Everest or on the Dead Sea. But the standard boiling point occurs at 1 atmosphere external pressure. All right, that was 17, and the answer to 17 was D. The vapor pressure at which boiling occurs is lower. 18. Which of the following statements about intermolecular forces is incorrect? Here's another negative. Which one is not true about intermolecular forces? These forces must be overcome in order for molecules to escape from the liquid state into the vapor state. That's perfectly true. There's nothing wrong with that statement at all. These forces are much weaker than intramolecular forces. That also is true. How do we know that? Intramolecular forces, those are the ones that hold atoms together in a molecule. And then intermolecular are the ones that hold molecules together. What if the intermolecular forces were stronger than the intramolecular forces holding the molecule together? If that was true, molecules just fly apart because the forces they're pulling on them from the outside would just rip the molecule apart. So we know that the intramolecular forces are stronger than the intermolecular forces. They are electrostatic in origin. Yeah, basically, they are. Whether it's ion-ion interactions, or dipole-dipole, or ion-dipole, or even London dispersion forces. They all have an electrostatic component. Or D, they occur within molecules rather than between. All right, that one is completely false. It's the other way around. These intermolecular forces are between molecules. All right, so D is the answer for 18. Skip down to 20. All right. Oh, I left the answer in this one. I should get that out of there. This is not supposed to be a key. Okay, in which of the following liquids would London dispersion forces be the predominant intermolecular force? Okay, recall that in every intermolecular interaction, London dispersion forces are there. They're always there. Whether they're significant or not depends on how strong the other forces are. The dipole-dipole, for instance, which is orders of magnitude stronger than London dispersion forces. So for the liquids where these London forces are predominant, we need to find one that is nonpolar, has no other, and non-ionic obviously, has no other forces to interfere with the London because they're so weak. So we look at our choices. Okay, we have this one, we have this one, we have this one, and we have this one. All right, how do we know dipole? How do we know that there's the potential for electrostatic that is excessive to London forces? You need an uneven distribution of electric charge that is permanent. Okay, so this one It's like that. And it has a dipole in that direction, right? So that one can't be it. This one is dinitrogen, right? You've got equal distribution because that's the same element as that one. They pull equally on electrons. The electron distribution is equal throughout. This would be a good candidate. That would be the London dispersion forces. H2S is like water. The dipole is like that. And IF would be a single bond. Fluorine is a stronger attractor. Okay, so all these others have dipoles except for nitrogen. All right, that was 2021. Which of the following descriptions apply to matter in the solid state? All right, this is fairly simple. 21. Definite shape and high density. That's true. It is a definite shape, and it does tend to have high density compared to the other phases. All right, cohesive forces dominate over disruptive. That's also true. Right? Potential energy wins in this molecule. In this form. Kinetic energy dominates. No. Kinetic energy is disruptive. More than one correct response. That's it. A and B are both true, so D has to be the answer. All right. So now I want to skip to 26. Just checking my time here. Okay, 26. Which of the following samples of gas would have a new volume of 3 liters if the pressure is decreased from 3 atmospheres to 1 atmosphere at constant temperature? Okay, so what are we talking about here? We're talking about a gas law, one of the gas laws, and we're also given a new volume of 3 liters, and we need to find the volume here, that would produce 3 liters if we decreased the atmospheric pressure from 3 to 1. So what 2 factors are involved? Pressure and volume, right? Pressure and volume. Boyle's law. Before and after. All right. What's the before condition? Well, let's say this is initial, and this is final. So initial conditions are what? Which of the following samples of gas would have a new volume of 3 liters? The new volume is 3 liters here. That's final. So we're looking for this one, right? So what's the final pressure? The final pressure is 1 atmosphere. So that means the beginning pressure is 3 atmospheres. All right, now we can answer the question. If this 3 times 1 is 3, correct? So this one has to be 3. So what value of volume would give you 3? 1. 1 liter. So which one of these gases is 1 liter? Helium, correct? That answers the question. This one doesn't satisfy. That one's wrong, so it can't be any of the others. That one is correct. 1 liter of helium will do it. For 26. All right, 27. Which of the following is a correct equation for the combined gas law? Right. Remember, I put the combined gas law up here before. PV over NT, 1, 1, 1, 1. Okay? So P2 V2 over N2 T2. There we go. So we got to look at each one. So if we solve for P2, then what's going to happen? Well, these two go over here, P1 V1 N2 T2, and that one comes over here, N1 T1 V2. Right? Is that correct? Well, notice what's missing. Moles are missing. So what they're saying is moles don't change. Right? So what we need to do is remove the moles. Now we can look at it. So P1 V1 T2. Nope, that's wrong. So it can't be that solution. Let's solve it for V2. So V2 would put T2 over here, but it would be P1 V1 T2. Look at that one. V1 P2. B is wrong also. All right, so let's solve it for T2. So T2 over here would come across there, and then it would leave this one, and that one. Right? That goes over here. This comes over here, and those two go over here. So P2 V2, P2 V2. None of them are right. They're all wrong. So there's no correct response. That's just the way it is. That was 27. Now let's see, what's the next one I have marked? I want to move down to 32. When the vapor pressure of a liquid equals atmospheric pressure, here's the one I was looking for. Here's the one I was looking for. When the vapor pressure of the liquid equals the atmospheric pressure, the temperature of the liquid equals what? It can't be 100 degrees, that's just water. The boiling point of the liquid? The temptation is to say that. And that it would be correct. Yeah, that one's correct. If that's all the information you're given, the vapor pressure of the liquid equals the atmospheric pressure, wherever it happens to be. If the atmospheric pressure is exactly 1 atmosphere, then it's the normal boiling point. That's the word I couldn't think of before, normal. The normal boiling point occurs at 1 atmosphere and only 1 atmosphere. The boiling point can occur at any pressure, any atmospheric pressure. Okay, so that was 32. And I'm just checking my time. We're still doing okay. 34. That's the next one. And we're still in chapter 7. Intermolecular forces differ from intramolecular forces in that what? They occur only in liquids? No. They are much stronger? No. The intramolecular are stronger. They occur only when hydrogen atoms are present? No. It looks to me Like this one has no correct answer either. None of those are right. Okay. So we work with what we're given, 35. Okay. In which of the following pairs of molecules would the first listed member of the pair have a higher boiling point than the second listed member of the pair? Okay. What do you need to increase the boiling point? You need stronger intermolecular forces, right? Okay, so let's check them out. A, B, and C. D is more than one is correct, and E is none are correct. So we only have to look at those three. HF and HBr. HF versus HBr. The first listed member has a higher boiling point. That's what we're looking for. Does the first member have the higher boiling point? F2, Cl2, and O2, and NO. Let's work from the bottom. O2 is like N2 before. London forces are dominant there. Whereas NO, let's see. I think it's like that. 1, 2, 3, 4, 5, 6, 2, 4, 6, 8. Yeah, I think it's that way. But the dipole moment is like that toward oxygen, right? So C is wrong. This one is the higher boiling point. How about this one? This might be a little more difficult. So what do we have here? We have like that, and we have like that. So which one of these would be? Well, look, they're equal. There's no dipole there, correct? Right? So we can't use that. Both of them are subject to London dispersion. So both of them are London. What's the difference? The difference is size. Difluoride is a very small molecule. Dichlorine is much, much bigger. And so what do we know about London dispersion forces? The larger the molecule, or the larger the atom, the more prominent, the stronger the London dispersion forces. Why? Because they've got more space to redistribute electron density. We saw that with noble gases, right? If we go neon, argon, krypton, xenon, we'll just use those four. The London dispersion forces increase this direction, and the boiling point increases that direction because you're getting bigger and bigger and bigger. And the only explanation for that is that with a larger atom, you can redistribute the electrons instantaneously, obviously, because London dispersion forces are not permanent. It's easier to redistribute electrons around a larger atom. Same thing for molecules. So this one has the higher boiling point. That one has the higher boiling point. How about these two? In these two, you have dipoles. So HF is going to be a dipole that way, and HBr be a dipole that way. But the dipole here is bigger because fluorine is more electronegative. It draws electrons to itself more strongly. So it makes a bigger negative charge on that side. Partial negative charge. So this one is the higher boiling point for the first member. Right there. And that's why. 35. Okay, so let's go to 40. All right. Characterize each of the three given statements as being true or false, and then indicate the collective true-false status of the statements using the choice. All three statements are true, two are true, only one is true, or none is true. Okay, so we have to look at each one and discern something about it. So number one, what does number one say? Both dipole-dipole interactions and hydrogen bonds are stronger than most single covalent bonds. One is false. Why? Because dipole and hydrogen bonds are intermolecular forces, and covalent bonds are intramolecular. They're always stronger than intermolecular. Right? So they got this one backwards. Number one is backwards. It makes it false. How about two? The value of the ideal gas constant is the same for all gases under ordinary conditions of pressure, volume, and temperature. That's true. That's why it's a constant. It doesn't change. The ideal gas constant does not change. What would change the ideal gas constant? I mean, that's not part of the problem, but I'm just curious. Can the ideal gas constant change? Yeah. If you change the units of pressure, volume, or temperature, then you have a different constant, because the constant units must cancel with the other variable units. So if you said pressure equal to torr, or volume equal to milliliters, well, you can't change the temperature because, well, yeah, you could. Absolute temperature, you could use the Fahrenheit equivalent of Kelvin, which is Rankine, but nobody uses Rankine. I'm just illustrating the point. If you change the units of measure, then the gas constant will change. But this statement, as given, is true. The value of the ideal constant doesn't change. How about three? Both condensation and freezing are endothermic changes. All right, what happens? If you go from condensation, you're going from what? Gas to liquid. So gas to liquid, right? You're going from a less ordered, higher kinetic energy down to a lower kinetic energy. So you got to lose energy to get there. Right? So you're going to lose heat. That's exothermic. Right? So we can stop there. Freezing the same way. Go from liquid to solid. You actually lose heat. You don't gain heat. We went the other direction. That would be endothermic. You have to add energy to make a liquid into a gas. Right? So 3 is false also. Right? So only 1 is true. C. Yeah, only one of them is true. And it's this one right here. All right, that was 40. Let's see, the next one I picked was 49. Here we go. For each of the physical state characterizations, select from the response list the physical state or the state to which the characterization applies. Okay, that's kind of a convoluted statement. What they want you to do is say, which one of these is the state where potential energy dominates over kinetic? Potential energy wins, right? I showed you that earlier on the board. So all we have to do is pick out the one that matches. Potential energy dominates only for solids. The attractive force overcomes the disruptive force, and you have a solid state. Right? So 49 should be B, the solid. All right, 50. For each of the physical state characters, oh, okay, so which one of these satisfies this condition? Particles are relatively close together. It could be two different states. We know that gases particles are way far apart. But the particles of solids and liquids are relatively close together. The difference is that the solid is ordered structure, whereas the liquid is not. The liquid molecules move past each other. But I think both liquids and solids are characterized by particles that are closer together. So that would be C for 50. Okay. All right, 51. I'm going to do that one too. Okay, consider the mathematical expressions for gas laws listed. Select the correct name for the law from the response list. All right, you should know this one by heart. Pressure, volume, before and after equal to each other. The product of pressure times volume is Boyle's law. All right. 54. Okay, how about this one? Consider the mathematical expression for gas laws listed. Select the correct name for the law. All right, we've got volume and temperature, but that's normally not the form that we see that expression. So let's write that one up here. V1T2 equals V2T1. Okay, this is like initial volume, initial temperature, final volume, final temperature. Can we rearrange that? Well, yeah. Put the ones together and the twos together. So this one comes over here, and this one comes over here. That looks more familiar. And that, in fact, is Charles' law. Right? That question was designed to confuse, unless you understand Charles' law, volume and temperature relationships. Then you can solve that and recognize it as Charles' law. 56. Let's see, that's scooting. That's still okay. Yep. 56. Consider the change of state descriptions. Select the name of the change of the state for the opposite of evaporation. Okay, so go back and in your mind's eye, consider what is evaporation. Evaporation is liquid to gas. So what's the reverse of that? From gas to liquid? Condensation. So that one, 56, is B, condensation. While we're here, let's do these others. Let's see, we missed one up here. Select the name of the change of state for an endothermic change. So we have to add energy to get it to change. So we would either go from a solid to a liquid, or a liquid to a gas, or a solid to a gas. Right? So what do we have? Well, endothermic process. Sublimation, a solid to a gas, that works. Condensation, now that's exothermic. Deposition is a gas to a solid, that's exothermic. Freezing, that's exothermic. Sublimation is the only one that works. It's an endothermic process. You have to add energy to the solid to make it change into a gas. Perfect example of that is dry ice, solid carbon dioxide. Okay, we did 56 already. Let's do 57. Oh, what's the name of the change of state for when energy is absorbed? That's endothermic. That's the same thing, right? Sublimation. So that didn't teach us anything new. Considering change of state, select the name of the change of state that involves liquid to solid. Liquid to solid. Okay. Solidification, I should have said freezing. Freezing is the accepted term from going liquid to solid. Freezing. Okay. Oh, we got another one. Change of state that involves both the liquids and the gaseous states. Okay, so what they're saying there is if the change involves liquid one direction, gas the other direction. So here we've got gas, but we don't have a liquid. Condensation, we have a gas going to liquid. So I think that is probably the answer. Yep, because deposition involves gas and solid, freezing involves solid and liquid. So condensation is the one that involves liquid and gas. All right. I didn't pick all of those, but I thought we were here, so we might as well make some sense of them. And the last one for this chapter I picked is 67. For the following intermolecular force descriptions, select the correct name for the response list. Permanent from the response list. Permanent electrostatic interaction between polar molecules in which no hydrogen is present. The generic is dipole-dipole interaction. That's what that means. If you have a dipole, one molecule, dipole, other molecule, they will interact in such a way to attract one another. But there's no hydrogen. Now, if there's a hydrogen and there's a highly electronegative atom attached to the hydrogen to give it that dipole, then it's hydrogen bonding. But hydrogen bonding is a subcategory of dipole-dipole. All right. All right, that's all for chapter 7. So we want to go to chapter 8. So I need to unshare this one, stop the share, and share chapter 8. And there's chapter 8 right there. Okay. So now I want to look at, starting with number 2. There we go. So remember the topics in number 2. They have everything to do with solutions. What is a solution? Characterize it. What can we do with solutions? What are concentrations of components and definitions of those components in solution? What are colligative properties involving solutions? We talked about actually 4 of those. Okay, a solution may contain what? Remember, I made a huge point of this one. A solution is composed of a solute and solvent. Right? You can only have one solvent. You can have one or more solutes. So which one is the solvent? The solvent is the major component, the one that's there in the largest amount. All right, so let's use that information to answer this question. Only one solvent, but many solutes. Well, that's it. That's the answer. Because the rest of them are wrong. Many solvents, but only one solute? No. One solvent, one solute. When it says only one solvent and one solute, that only is what makes it false. If it just says one solvent and one solute, yeah, you can have that. But only one solvent and many solutes, that is the best answer. All right, so 2 is A. Let's see. Scooch that back a little bit. Number 3. Which of the following statements concerning a saturated solution is incorrect? Here's a negative question. Which one is wrong? Which one is false? Undissolved solute must be present in a saturated solution. What does that mean? For 3, saturated solution. Let's look at what a saturated solution would be. You have a solvent, and you have at least one solute in that solution. But down here, you have undissolved solute. Now, that's not always the case. You can have a saturated solution without this in the bottom, but if you do have some in the bottom, then you know it's saturated. Undissolved solute must be present. No, not necessarily. So that could be the false one. All right. Undissolved solute may or may not be present. That's true. Undissolved solute, if present, is continually dissolving. That also is true. We have an equilibrium situation. So this is going into solution at the same time solute is returning to the solid. Right? That is an equilibrium situation. So that statement, C, is true. It's continually dissolving. Undissolved solute, if present, is in equilibrium with dissolved solute. That's another way of saying C. So the only one that's false is undissolved solute must be present. No, doesn't have to be present. You can have a saturated solution. You can form a saturated solution with solute in the bottom and then filter it out. And you're left with a saturated solution. All right, that was 3. How about number 6? For which of the following types of ionic compounds are most examples insoluble in water? All right. So for this one, you either need to know the rules or you need that chart, right? And then you look at that chart and say, all right, these are all anions, negative ions. So you go down the left-hand side and find your negative ion, nitrate, you follow it across. Are most of those soluble or insoluble? Well, nitrates are all soluble. So A is not the answer. We need to find the one where most are insoluble. Sulfates, how about sulfates? You look at the sulfates and find that most of the sulfates are also soluble. There are a few that are insoluble, but most are soluble. How about hydroxides? You look at the hydroxides and you find that most of the hydroxides are insoluble. Which one would be soluble? Potassium, lithium, sodium, right? All the alkali metal hydroxides are soluble. And the chlorides. Most of the chlorides are soluble. There are just 3 that are insoluble. Silver chloride, lead-2 chloride, and let's see, I painted myself into a corner. Which one's the third one? I think it's 10. 10-2 chloride. Look it up. Most chlorides are soluble. Hydroxides are mostly insoluble. So C is the answer for number 6. All right, so let's, what's the next one? Number 11. What's the molarity of a solution containing 16.7 grams of ammonia in 1.5 liters of solution? All right, so what are we given? Well, the question is, what's the molarity? What we're given is mass. 16.7 grams of ammonia. And the volume of the solution, right? That's important for molarity. It has to be the volume of the solution is 1.50 liters. So can we calculate this? This is equal to moles per unit volume. That's not moles. So we got to change it, don't we? We need something that will cancel mass and give us moles. And like I've said before, whenever you have mass in moles, grams and moles in a quotient, that's molar mass. So what's the molar mass of ammonia? Well, nitrogen is 14.01. You know, look it up on your periodic table. Hydrogens are 1.01 times 3. So that's 3.03. That's 17.04 grams per mole. Okay? So how many moles is that? 16.7 divided by 1704 is 0.980. Now we can calculate this. Divided by 1.50 liters. That's the definition of molarity. So I'll take that number and divide it by 1.5. I get 0.653. 0.653 molar. And I'll just point this out. By the way, the answer is B. Whenever you have a decimal with no whole number attached to it, you better put that 0 there in front of the decimal. If you don't, that's what I call an orphaned decimal. And I don't tolerate orphaned decimals. If you don't put a 0 there, your answer's wrong. But of course, with multiple choice, it's already there. But if you submit any kind of a report where you have to write the answers in, if you leave that 0 off, that's a wrong answer. You put that 0 in there, that's a placeholder. That says that there are no ones or anything bigger than 1. And it also protects that decimal from being mistaken as the period at the end of a sentence. All right. So that was number 11. Let's go down to 14. If 145 milliliters of 2 molar KOH is diluted to 1.15 liters, the resulting solution contains how many moles of KOH? All right. So what are we given first? We're given 145 milliliters of this 2 molar KOH. Okay, extract the information, put it up there. We're going to dilute it to, so this is the first volume, the initial volume that we take out of this concentrated solution. Now we're going to dilute it to 1.15 liters. So the final volume is equal to 1.15 liters. Okay. The question is, how many moles of KOH are in the final solution? Remember the discussion of dilution, where I said M1V1 equals M2V2, or M concentrated, volume concentrated equals molarity dilute times volume dilute. Why does that formula work? There's something that's common to both of them. Notice that molarity times volume is equal to what? There's your definition. Molarity times volume is moles. So if you take this many milliliters out of that solution, you got a certain number of moles. So how many moles do you have when you get down here to this diluted one? The same number of moles. You don't need that volume. You just need this one that tells you how many moles you have going into the diluted solution, because the moles are the same, both sides. The thing is, that unit of measure is wrong for this calculation. So in order to do this calculation, we need liters. So how many liters is 145 milliliters? 1, 2, 3. 0.145. Okay, now, so what is that answer? 0.290 moles. Correct? Right there is your answer. So notice what this problem is like any word problem. It's designed to confuse. If you don't know your stuff, then any word problem will spin your head around. If you know the material, then you notice that all you need is this volume and that molarity to answer that question. You don't need that information. That's what I call blue smoke that they blow in your face to confuse you. So the moral of that story is, if somebody tells you that multiple choice tests are easier than essays or short answers or fill in the blank or whatever, you can call them a liar. Multiple choice questions are inherently difficult because they are designed to confuse. Number 15, a colloidal dispersion. All right, remember we talked about different types of mixtures. You can have a heterogeneous mixture in which the composition is different everywhere you look. Or you can have a homogeneous mixture, in which case everywhere you look the composition is the same. Well, typically a homogeneous mixture is a solution, but we discovered one type of homogeneous mixture that's not a solution, and that is the colloid, the colloidal dispersion. It's not a solution. And the way we tell, well, theoretically, a colloid, the suspended particles will remain suspended indefinitely based upon their particle size. They're very small particles, but they don't form a solution. And the way we tell the difference between a colloid and a solution is the Tyndall effect. We shine a light through it. You see the light go in, you can see the light go out, but you don't see it inside the solution. If it's a solution. If it's a colloid, you see that light beam going straight through your solution. The reason for that is the colloidal particles, what? Are large enough to scatter light. They're not large enough to be seen with the naked eye. They're not even large enough to be seen with microscopes. Too small. But you can see the light scattering. That's the Tyndall effect. All right. 16. Let's do 16 also. Flip my page. Compared to pure water, a 1 molar sugar water solution will have what? A lower vapor pressure. Is that true? Yeah. Yeah, we'll have a lower vapor pressure. The and my mind's gone blank. I was trying to think of the name of the law. Raoult's law determines vapor pressure of mixtures. So this lower vapor pressure is due to the fact that this 1 molar sugar content interferes with the vaporization of water molecules by basically 2 different ways. So this is 1 molar sucrose, which is table sugar. All right, so what has to happen for vapor pressure? You got to have molecules here of water escaping. Right? Well, suppose the water molecules are attracted to the sugar, which they are. Then that impedes their vaporization and reduces the vapor pressure. Also, you've got sugar molecules up here at the surface interfering with molecules, water molecules below them reaching the surface. So you have two effects there that are impeding the vaporization of water, which would lower the vapor pressure. Okay, so A, C, D could be it. B is out. It won't happen. Let's look at the second one. Lower the boiling point. That's false. When you add a solvent, a solute to a solvent, it increases the boiling point. Right? So A is out. C is the only one that has met conditions up to this point. Higher boiling point, and yes, lower freezing point. You lower the freezing point, you increase the boiling point. Those are colligative properties that are based upon the concentration of the solute. And it doesn't matter what the solute is. In fact, all of these are colligative properties. Vapor pressure, boiling point, freezing point. The only one we haven't mentioned in this scenario is osmotic pressure. So what would the osmotic pressure be? Well, as measured, the osmotic pressure increases when you add a solute. But then you have to understand the definition of osmotic pressure. The higher the concentration of the solute, the higher the osmotic pressure. And that's because the semi-permeable membrane, let's do it here. The semi-permeable membrane here, right there, with, say, a 1 molar sucrose solution in there, and this is water, then the water tends to migrate here, and from this level, you build up a higher level in there, and that translates into a pressure. So the higher the concentration of the solute, the higher the vapor pressure, osmotic pressure. Okay, we'll probably get to a question that uses that information, so don't throw it away yet. 17, I want to look at also. 17. Um, 17. Instead, stop and think for a second. The one law we haven't talked about is Henry's law. Henry's law addresses the solubility of a gas in a liquid under varying conditions of pressure. Increase the pressure, you increase the concentration of the gas in solution. Okay, so back to 17. What's the freezing point for a solution containing 1 mole of sodium chloride dissolved in 1 kilogram of water? Right, you're going to need some extra information here, right? And if this type of question appears on the exam, that information will be given in parentheses. But in this environment, you can look it up, right? Because you're not taking a test. So we're looking for what's the freezing point of this solution. What's the temperature of the freezing point of that solution? And let's characterize the solution. 1 mole of sodium chloride. So the number of moles is equal to 1 mole of sodium chloride. And the mass of the water is 1 kilogram. Okay. Now, what values apply here? Well, you need the formula, right? If you're going to calculate this T, we need a formula that relates a change in temperature with our constant value. And in fact, that's the freezing point depression constant. And then you need molality, moles of solute per kilogram of solvent. Now this is, I should write mass, so we don't get it confused with molality. Okay, so do we have the information we need? Well, we have kilograms and we have moles, right? So we do have the information. But this is molality of particles. If you have an ionic solid that dissociates, you need a correction factor, the Van Hoff value, I. I is equal to 2, because this becomes sodium and chloride ions. So we need another factor in here. You need that correction factor, the Van Hoff factor. Okay, now that we have that information, what's the molality of this solution? Well, the molality of sodium chloride is 1 molar, 1 molal, right? So M equals 1 mole of sodium chloride per 1 kilogram of solvent. So that's 1. This is 1. I is 2. So what's K, right? K, you have to look it up, or it's given to you in a test. 1.86 degrees C per molal. 1.86 degrees C per molal. Okay? So what's the change in temperature? 2 times 1.86 times 1. So this would be 217 and 3. So that's the change in temperature. What kind of change? In this solution, we're talking about freezing point depression, right? So what's the freezing point of pure water? 0 degrees, right? So freezing point, oh, here it is. Freezing point then is a depression. So 0 degrees minus 3.72 degrees C. So you're going to decrease the freezing point of water by that factor, that change, 3.72, which means the answer is D, right there. Okay, so the trick to this one is recognizing that fact right there. If you don't, then you're going to put this answer in and get it wrong. So that was 17. Let's see, 19. Crenation of red blood cells. What does that mean? Crenation, the normal blood cell is like that, right? Well, it's kind of a hockey puck that's been pushed in on both sides. What happens when you put it in pure distilled water? Water goes in and the cell explodes. What if you put it in a 1 molar sodium chloride solution? water moves out, and you get a wrinkled cell, which is a crenated red blood cell. So, what type of solution is this that you put it in? It's hypertonic. Tonicity refers to the concentration of the solute relative to the other side of the membrane, which is a cell in this case. So this solution is hypertonic to that solution because it has higher concentration of solute. And it causes water to move out of the cell. All right. So that was C for 19. Check my position here. There we go. 20. We'll look at 20 also. Which of the following solutions is hypertonic with respect to blood? Okay, this is going to require some memory. All right, what two values? We discussed these in the lecture. What two values are isotonic to your body fluids? Well, if we're talking in terms of sodium chloride, it's 0.9% mass volume, sodium chloride. That's not exactly isotonic, but it's very close. So we assume that it's isotonic. What about glucose? Glucose is 5% mass volume. Okay. Now, you will often see this as D5W. D stands for dextrose, which is essentially glucose. 5 is the 5%, and W is in, I'm not sure if that's water, D5W water, or D5W by weight. It's probably by weight. D5W is isotonic. Okay, so now we can answer the question. Which one's hypertonic? Well, 0.5 and 0.7% are less than 0.9, so they're hypotonic. 4.5 is less than 5%, so it's hypotonic. 7.6 is greater than 5. So that's your hypertonic solution. All right, 2021. Which of the following statements about solutions is correct? Okay. A solution is a homogeneous mixture. Well, yeah, that's by definition, right? So more than one is correct? Okay, so we got to look at all of them. It is possible to have solutions in which both solute and solvent are solids. Yeah. That's true. Example, brass. Brass is a solution of nickel and copper, primarily. Sometimes they put other things in there. So more than one is correct, right? So actually, we don't have to go to C. Solutions readily separate into solute and solvent if left undisturbed for 24 hours? No. Solutions do not separate. That's heterogeneous mixtures that separate. Okay, so the answer there is D. More than one correct response. All right, 22. I want to look at 22 also. A crystal of solid sodium chloride is placed into an aqueous sodium chloride solution. Aha. And we'll do some detective work. So we've got a solution, sodium chloride in aqueous solution. Okay. Now we're going to put solid sodium chloride in there. Okay. What we observe is that most of the sodium chloride we put in there dissolves, but not all. It leaves a little bit of solid on the bottom. So what does that mean about the original solution? Was the original solution saturated? No, because you can put more solid into it. So it's unsaturated. And obviously it's not supersaturated. What would happen if it were supersaturated and you put some sodium chloride in there? You'd actually get more sodium chloride on the bottom than you had when you put it in, because it would precipitate out of solution. Unsaturated is the answer. Well, unsaturated, it's also, we can't say that it's dilute. The reason we can't say it's dilute is if it were dilute, all of the sodium chloride would dissolve. But some of it was left over. It was very close to saturation. It was still unsaturated, but it was very close. It would have been considered concentrated, not dilute. So B is the best answer for that one. All right, that was 22. Let's see, where do we go from here? 24. Consider the following substances and their polarities. Okay, so we've got these different molecules, A, B, C, and D. So A is polar, B is polar, C and D are both nonpolar. C and D, nonpolar. Those are the facts. Now, which one of these is true? More than one could be true. Okay, so we got to look at all of them. A is more soluble in C than it is in B. A is more soluble in C than it is in B. No, like dissolves like. A is more soluble in B than it is in C. So A is false. How about statement B? C is more soluble in D than A. C is more soluble in D than it is in A. That's true. Like dissolves like. So that one's true. What's the third one? D is more soluble in B than C. D is more soluble in B than C. That's false. Okay, so only one of them is true. That's B. Right there. All right, next one. Let's skip way down to 34. Which of the solutions has an osmolarity of 3.0? 34? 34. Okay. Which one has an osmolarity of 3.0? It needs to be 3.0 osmolar. Okay, so what you need is to understand how the molecules behave. So let's take each one in turn. Since we have to look at all of them, D says more than one is correct, E says none of them are correct. So we have to look at each one. So let's look at A, B, and C. A is 4 molar glucose. 4 4 molar glucose. Does glucose dissociate? No, not in water, stays intact. So what you put in here is 4 molar is 4 osmolal, right? So it can't be that one. How about this one? 2.0 molar sodium chloride. So what is its osmolarity? It dissociates into 2, that one and that one. So it is 4.0 osmolar, not osmolal, osmolar. So that was not it. Let's see if C satisfies. 1.0 molar sodium phosphate. So what does sodium phosphate do in solution? Breaks apart into 3 sodiums and 1 phosphate. So that means 4 osmolar. None of them are correct. So E is the answer. Okay? Check my position here. There we go. That was 34. Oh, 35. I'd like to look at that one also. In which of the following pairings are the terms closely related? Okay. So we got to look at these 3. A, B, and C. So the first one has hemolysis and hypotonic solution. Hemolysis and hypotonic solution. All right. We know what a hypotonic means. That is, outside the cell, the concentration of the solute is lower. So water tends to move into the cell. The concentration is higher inside the cell of the solute. Or another way to look at it is the cell is here, and if this is hypotonic, what's the concentration of water? The concentration of water here outside is greater than the concentration of water inside the cell. That may be helpful looking at it that way. Then if the concentration outside the cell is greater than inside, water's moving in. Okay, now what does hemolysis mean? Heme refers to blood. And lysis is variously interpreted as cut or split. The cell, the blood cell, splits. It breaks. It disintegrates. That's what will happen if you pump water into that cell to the breaking point. So those 2 together are correct. That is true. So this one is true. How about B? Hypertonic, higher osmotic pressure than within the cell. Hypertonic is is higher osmotic pressure than within the cell. So it has higher osmotic pressure outside the cell than it does inside the cell. That's true. That's what hypertonic means. Isotonic solution, crenation. Do you get crenation with the isotonic? No, that's false. So two of the above are true. More than one correct response. So D would be the answer for 35. Let's see here. 42. Let's go down to 42. 42. Stop there. And let's make some space. "42. Characterize each of the three given statements." This is 1, 2, and 3 as being true or false. All right, this is like that previous one we did. So we got to look at each one, each three, and decide how many of them are true. So what does 1 say? Addition of 40 milliliters of water to 10 milliliters. Add 40 milliliters to 10 milliliters of 8 molar sodium hydroxide. To 10 milliliters of 8 molar sodium hydroxide. So what do we do with that one? Oh, and it would produce a 2 molar sodium hydroxide solution. That yields 2 molar sodium hydroxide. Is that true? What are we going to use here? What type of expression? Before and after? This is a dilution problem. So you need to know initial, not yields, but equals final. Right? So what's the initial molarity? 8 molar. What's the initial volume? 10 milliliters. And notice on these ratio problems with molarity, you don't have to change the units. The units can be 10 milliliters. What's the final molarity? Well, we want to see, is it equal to 2? So it's really unknown at this point. And the final volume is 40 milliliters added to 10 milliliters. So the final volume is 50 milliliters. All right, solve for this one. So that's 8 times 10 is 80 divided by 50. Right? Is that going to be 2 molar? No, 50 into 80 is going to be less than 2. If this were 40, well, yeah, it would be 2. But it's 50. So number 1 is false. Okay, let's look at number 2. Number 2, Henry's law. Okay, here's Henry's law. Henry's law. What is Henry's law? Well, the concentration of your gas in solution is proportional to some constant we call H for Henry times the pressure. If you know what the pressure is and you have Henry's constant, then you can determine the concentration of the gas. And it doesn't matter what the gas is. Actually, it does matter what the constant is. The constant changes with the gas. Yeah, the constant changes with the gas. Because some gases are more soluble at the same pressure than others. All right, so that's Henry's law. Is a pressure solubility relationship for gases in liquids. That is true. That's what that means. 3, boiling points. Boiling points are the basis for the solubility rule, like dissolves like. Temperature, boiling point, like dissolves like. Let's think about this. What is it that like dissolves like means? It refers to polarity. Right? So what can we say about boiling point? Well, the boiling point does change with polarity of the molecules. So we could say that 3 is true. But you would have to really stretch to make that comparison. Boiling points are the basis for solubility. It's really, when it gets right down to it, the intermolecular forces that are the basis for like dissolves like. So we really can't say that 3 is true. We have to say that that one's false. So really only one of them is true. Okay, just one. All right, so let's see, what else we got? 46. Let's see how we're doing on time. Oh, I'm over time already. All right, so I'm going to continue. Since there's nobody here anyway but me, I'll just keep going until I finish talking about the ones I want. For some reason, I got it in my head, I had till noon, but I don't. We go from 9 till 10:50. So let me look at 46. Maybe I can speed it up a little bit. For the set of ionic compounds, sodium nitrate, potassium nitrate, ammonium nitrate, choose the correct characterization of their solubilities in water. All right, here's where you're going to need the solubility chart. Right? If you don't know the rules, then you go to the solubility chart. The rule says that all nitrates are soluble, period. Well, in fact, all sodium salts and all potassium salts and all ammonium salts are soluble too. So everything here is soluble. All 3 salts are soluble. That's 46. How about 47? For lithium chloride, silver chloride, and magnesium chloride, how many of these are soluble? Not all 3. Most chlorides are soluble. That's true. Lithium and magnesium chlorides are soluble. Silver chloride is not. 2 of the 3 salts are soluble. So 47 is B. How about this one? Barium sulfate, barium carbonate, barium hydroxide. How many of these are soluble? So here we've got barium's the same. It's an alkaline earth. The hydroxides are insoluble, right? That's definite. I know that one. How about the carbonates? Most carbonates are insoluble also. The sulfates, though, are soluble. There are only a handful of sulfates that are insoluble. So one of these is soluble, right there. That's barium sulfate. Let me check that to be sure. I need my, hold on a second. There we go, there's my chart. I just want to be sure. So if you have your chart handy, like this one right here, there, you just go across the top until you find barium, which is here, and you go down and look. Barium sulfate is insoluble, pardon me. Barium hydroxide is soluble. So barium hydroxide is an exception to the rule. All right, so I got that wrong. Barium sulfate is insoluble. Barium carbonate is insoluble. Right. Barium sulfate, hydroxide, is soluble. Right. Most hydroxides are insoluble, except for barium, potassium, and sodium. Those three are soluble. Okay, I should have known better. Anybody who's had a barium enema as a contrast agent for an X-ray of your colon, you know that barium sulfate is not soluble. Barium is a huge atom, and it absorbs X-rays that are shown through your body. So if you've got barium sulfate in your colon, then it's going to absorb X-ray energy and give a beautiful outline to the colon. But it's insoluble, so your body doesn't absorb any of the barium or the sulfate, right? So that makes it safe to use. If it were soluble, then your body could pick up that barium and you'd have metal toxicity in a hurry. So that's why they use barium sulfate. Not that the experience is one I'd want to repeat, but at least it's safe. All right. So the answer to that one is only one of these is soluble. Wait a minute. Did I say? That's right. Only barium sulfate is soluble. How about 49? For the set of these compounds, calcium sulfate, calcium bromide, and calcium carbonate, how many of these are soluble? Well, calcium sulfate this is anhydrous calcium sulfate, but calcium sulfate with two waters attached. That's gypsum. And you know, if you get gypsum board wet, it just falls apart. It doesn't dissolve. Calcium carbonate is limestone, right? And it doesn't dissolve either. Calcium sulfate and calcium carbonate are insoluble. Calcium bromide, on the other hand, is definitely soluble. In fact, it follows the rule halogens. All the halogens are soluble except for a few exceptions. So only one of these salts is soluble. That's calcium bromide. All right. How about 50? Well, let's see. Let's look at it. There's aluminum nitrate, right? All the nitrates are soluble, right? So that one's soluble. Aluminum hydroxide. How about hydroxides? right? That's insoluble. That follows the rule for most hydroxides are insoluble. Aluminum phosphate. How about aluminum phosphate? Well, the phosphates are all insoluble except for sodium and potassium. Right? So the phosphate's insoluble. The only one that's soluble is aluminum nitrate. So there you have again, one of these salts is soluble. Okay, that was so much for solubilities. 51, I do want to look at 51. For a solution composition of 10 grams of solute and 90 grams of solvent, choose the correct numerical concentration, mass. So how do we do mass? If we've got 10 grams of solute, how do you do percent mass? Mass means mass of the solute on top, mass of the solution on the bottom. So that means you have 10 grams on the bottom plus the solvent, which is 90 grams. Right? So that's 10 divided by 100 times 100. That's 10%. Well, I should write it this way, 10.0%. Right? There it is, percent mass. 10.0. All right. 57. Choose the correct numerical value for the molarity from the response list. This was 57. All right. So let's see. We need to calculate molarity. Do we have the information we need? 0.1 mole of solute, 1 liter of solution. That's it. You can do that one in your head. That one is 0.1 molar. Right there. And let's see. Do I have any more? Nope, that's it. I mean, there are others, but those are the only ones I picked out as unique. So don't forget to print the periodic table and the solubility chart before you open the exam in Lockdown Browser. Then you'll have those with you. Any other information will be provided by the problem, unless you're supposed to have it memorized. And if you work all those homework problems, then you'll find out what information you need to know. Right? If you don't work any of the homework problems, then well, I'm not going to tell you what I'm thinking. It's not nice. All right. So that's it. That's it for our review. And next Friday will be the deadline for that exam, exam 3. And then we'll start new materials for the final exam, the last 2 chapters, which would be 9 and 10, I believe. All right, so I'm going to stop this share and close the meeting.